Welcome back, friends. In this session, I am going to discuss more numericals of the first CPU scheduling algorithms, which is first come, first serve. So, here is the first question I am going to discuss here. Let's assume that there are 7 processes given and arrival times of these 7 processes are given, as well as the burst time is also given. The question is calculate the average turnaround time, waiting time, schedule length and the throughput of the system. Also calculate the percent CPU idleness. Take your time and try to solve this. I'll explain the solution. So here is the solution for this question. As the criteria of FCFS is arrival time, so let's sort this table first according to the arrival time. So I have sorted this. So according to this table, I see that process P4 and process P6 arrives at time t is equal to 2. So I have written them at the beginning of table, followed by process P1 at 4, process P7 at 4 and so on. Once you sort this table, let's draw the Gantt chart for this table now. So let me take here the CPU timeline starting with 0. I'll mark the arrival processes below and completed processes above the timeline. So the table says that at first process, which is P4, is arriving at time t is equal to 2. So from 0 to 2, the CPU is going to be idle here. And at time t is equal to 2, two processes are arriving, P4 and P6. So here the question is which one to schedule out of P4 and P6. So let's follow the chronological order and schedule the P4 first. So P4's burst time is 1 time unit. So from 2 to 3 it will take the CPU and at time t is equal to 3 it's going to complete. At time t is equal to 3 I am going to schedule P6 because P4 has already completed, and P6 again is going to take 1 time unit and at time t is equal to 4 it's going to complete. At this point, both processes have completed, but at the same time at time t is equal to 4, two more processes are arriving, P1 and P7. So at time t is equal to 4, P1 and P7 are arriving. So out of these two processes, I am going to schedule P1 first. P1 is going to take 3 units of time, which is the burst time. So from 4 plus 3, that is 7, is going to run and completes its execution. And while it is doing its execution, at time t is equal to 6, process P5 is arriving. Look at the table also. At time t is equal to 6, process P5 is arriving. At time t is equal to 7, we have two processes, that is P5 and P7 waiting for CPU. So out of these two processes, P7 came first. That's why I'm going to schedule the P7 here. P7 is going to take 2 units of time. So it will complete at t is equal to 9. At time t is equal to 9, I have only one process, that is P5. So I'm going to schedule the P5 here up to 11 because its burst time again is 2 units of time. At time t is equal to 11, it's going to finish. At this moment, I don't have any process in the system. That's why CPU remains idle till next process arrives, which is time t is equal to 12. So at 12, P2 is arriving and let's schedule the P2 at this moment. It is going to take 3 units of time and it will run up to 15. So at 15, it's going to complete. Again at time t is equal to 15, system has no process to schedule in CPU. CPU remains idle till process P3 arrives at time t is equal to 18. And we know that this is the last process which is arriving. So I'm going to allocate the CPU to process P3 and it completes at 19. So that's how we have completed the Gantt chart for this particular example. Let's do some calculation. Let's mark the completion time of all the processes here. Process P4 completes at time 3. Process P6 completes at time 4. Process P1 completes at time 7. Look at the Gantt chart. Process P7 completes at time 9 and so on. So I have marked all the completion times here, the ones which are shown in the green color. And let's calculate the turnaround time. This formula is completion time minus arrival time. So 3 minus 2, 1. 4 minus 2, 2 and so on. The addition of all turnaround times is 20 and 20 divided by, we have 7 processes. So 20 by 7 is 2.85, which is the average. Let's calculate the waiting time. Waiting time is given by turnaround time, that is total time spent minus how much time it actually did the execution in CPU. So 1 minus 1 is 0. You can observe in the Gantt chart also, the moment P4 arrives, it is directly scheduled to CPU. So P4 has not waited even 1 unit of time. That's why the waiting time of P4 here is 0. So these are all the waiting times of all the processes. Addition is 7 and 7 by 7 is the average waiting time is 1. Let's calculate other factors. The schedule length. The last process is completing at time t is equal to 19 and the first process is arriving at time t is equal to 2. So that's why the schedule length is given by 19 minus 2, which is 70. Note here that we are not considering 0 as our start time but 2 as our start time because first process has arrived at 2. The next factor is throughput. The formula is N by L. So there are 7 processes divided by total time required is 17. The fraction is 0.41. Let's calculate the percent CPU idleness. The formula is given by how much time the CPU remain idle out of the total schedule length multiplied by 100. So I can see that in entire 17 time units for here 1 time unit and between 15 to 18 that is 3 time units. So total is 1 plus 3, that is for total 4 time units the CPU has remained idle out of the schedule length. Don't consider again this idle time here. So out of 17, 4 time units the CPU was idle into 100 gives us the percent CPU idleness, which is the 23.53 here. Let's take another question. In this question, I have introduced the I/O burst time of the processes also. Let's look at this chart. So here, each process performs some execution in CPU first. After completion, its first burst, CPU burst, it will go for input output, and after completing the input output, it will again ask the CPU for some execution. So in this sequence of burst time, that is CPU burst time of 4, followed by I/O burst time of 10, and again 1 time unit it will require in CPU, and then the process will complete. Remember that we are going to draw the Gantt chart of CPU. So these are the 4 processes arriving at these times and all the burst times and I/O burst times are given. And with this data, let's calculate these factors, average turnaround time. 2 points are given here. Consider that each process will perform the I/O on different IO devices. Meaning is that, let's assume that process P1 will start the IO after completion of these 4 time units. So while it is doing the IO on some IO device, let's say a keyboard or a CD writer, when the process 2 asks some IO device, the consideration you have to make is process P2 will ask some different IO device than P1's. So that's how we have to consider here the processes are doing the concurrent IOs, or you can say the parallel IOs on different IO devices. So processes won't wait for each other for IO device. But certainly processes will wait for each other to get the CPU, because we have only one CPU for all processes. Other factor is given, which is the context switching time, which is also known as scheduling overhead, denoted by delta here. What is the meaning of this? We have learned in the previous sessions that while doing the context switching of 2 processes in CPU, OS takes some time actually, and that time is the overhead. So for one amount of, so here the delta is given as 1. So if some process is running in the CPU and other process comes and asks for the CPU, if I want to load the new process in CPU has to spend, OS has to spend 1 time unit to actually start the execution of that next process. So 1 time unit will be vested between the 2 process. So, and calculate the turnaround time, average turnaround time. So let's solve this numerical. Let me draw this Gantt chart here, starting with time t is equal to 0. So at time t is equal to 0, process P1 is arriving. So let me mark it here. At this moment, I have only one process in system. So let's schedule that process. But remember, we have to introduce context switching time here also. So before I schedule any process to CPU, I have to allocate 1 time unit here. From 0 to 1, I am allocating the delta for context switching time, and at time t is equal to 1, actually the process P1 is going to start the execution. So the first burst time P1 needs is time t is equal to 4. So from 1 to 5 it is going to execute. At time t is equal to 5, it will go for IO device to do the IO. So let me show here P1's IO start at time t is equal to 5, and it needs 10 units of time in IO. That's why 5 plus 10, that is at time t is equal to 15, it is going to complete its IO, and at time t is equal to 15, it is going to ask the CPU one more time. Okay. So whenever we will reach to time t is equal to 15 in the CPU Gantt chart, we will consider that process P1 will again come in the system to ask for the CPU. Alright. So let's continue. So while P1 was doing the execution, process P2 arrives at time t is equal to 2, and process P3 arrives at time t is equal to 4. And at time t is equal to 5, process P4 also arrives. At time t is equal to 5, I have only so process P1 is doing the IO, and at time t is equal to 5, I have to decide out of these 3 processes P2, P3 and P4, which one will be scheduled. So now we are under the category, we are solving the example of first come first serve. So the answer is very simple here. P2 has arrived first, so I am going to put 1 delta from 5 to 6, and at time t is equal to 6, I am going to schedule the process P2. P2 is going to take 4 units of time. So from 6 to 10, it will do the execution in CPU. At time t is equal to 10, it will go for IO. And it is going to take 15 time units. It's given in the table, 15 time units for doing the IO. So 10 plus starting at time t is equal to 10. From 10 plus 15 time units, that is at time t is equal to 25, it is again going to come in the system and ask for the CPU. So let's go ahead at time t is equal to 10 while these two processes are doing the IO now. So P3 and P4 has not get the chance in CPU yet. So at time t is equal to 10, I have P3 and P4 waiting to get CPU. So I'm going to put one delta here again, and at time t is equal to 11, let's schedule the process P3 which is in the queue now. It just requires one time unit in the CPU, and after which it is going for IO. So starting with 12, it will take 25 time units in the IO, and at time 12 plus 25, that is at time t is equal to 37, it is again going to ask the CPU. Now first three processes has completed first burst time and also doing the IO. At time t is equal to 12, I have one more process, that is P4, waiting to get chance in CPU. So let's schedule the process P4 here by putting a delta first and then process. So from 13 to 17, because it requires 4 time units in the CPU, and at time t is equal to 17, it is going for IO. And the table says that it requires 3 time units to do the IO. So at time 20, it's again going to come back and ask for the CPU. Now observe that between 13 and 17, while P4 is doing its execution, P1 has already completed its IO. So let me show it here. At time t is equal to 15, P1 has came back and it is asking the CPU again. Remember that FCFS is non-preemptive. That's why when one process is under execution, even if at time t is equal to 15 P1 is arriving, we are not going to halt the execution of P4. First let the P4 complete, and then we will schedule the P1 here. So when P4 goes for IO, there is only one process in the system, which is P1 now, which has just arrived again, and P1 needs 1 unit of time in the CPU, so that's why the process will take only 1 time unit, and at time t is equal to 19, process P1 completes here. Let's go further. Now at this moment, at time t is equal to 19, I don't have any process to schedule to CPU, because it will come at time t is equal to 25, it will come at 37, and it will come at 20. So from 19 to 20, the CPU is going to remain idle. And at time t is equal to 20, process P4 is going to complete its IO, and one more time it's going to ask the CPU. Let's schedule the process P4 now by putting a delta first. Now P4 needs 2 time units in CPU. That's why I have given here 2 time units, and at time t is equal to 23, process P4 is going to complete. Now remember that P4 and P1 has completed their IO as well as the last burst time also. And at this moment, 23, I don't have any process in the system, because process P2 is still doing the IO and process P3 is still doing the IO. So from time t is equal to 23 to 25, the CPU is going to remain idle. At time 25, P2 is going to complete its execution in IO, and it's going to ask the CPU. So at time t 25, we are going to schedule the process P2 one more time, and P2 needs 2 time units in CPU. So from 26 to 28 it will do the execution in CPU and it will complete. At time t is equal to 28, again I don't have any process because the next process, which is P3, going to come at 37. So from 28 to 37 the CPU is going to remain idle. And at 37 finally we have P3 in the system. Let's put a delta here, 1 unit of time, and it takes 3 units of time in CPU, the burst time of P3 here. And at time t is equal to 41, process P3 also completes. Let's calculate the factors. The completion time of process P1 is 19, P2 is 28, P3's completion time is 41, and P4's completion time is 23. Let's calculate the turnaround time, which is 19 minus 0, which is 19, 28 minus 2, that is 26, and so on. The summation is 100 here divided by 4, and 25 is the average turnaround time. And here is the waiting time, that is the formula is TAT minus BT. 19 minus, so here BT is the summation of all these BTs here I am considering. Don't just consider 4 and 1, consider IOBT also. So the summation is, the sum is 4 plus 10, 14 plus 1, that is 15. So for 15 units of time process is doing some task, whether it's in CPU or in the IO device. And the total time spent by the process is 19. So 19 minus 15, which is 4 here. Similarly, calculate the waiting time for all the processes, and the average is 6.5 here. Schedule length is 41, is the last, the completion time of last process, and first process has arrived at time t is equal to 0. So that's why 41 minus 0 is 41 here. Percent CPU utilization, let's calculate. So what is the percent CPU utilization is whatever time you see in the shaded portion, that is all deltas and idle time. Excluding that time is actually the CPU utilization. So out of the total length that is 41, the idle time is 12. Let's calculate here. 1 time unit here, 19 to 21. 2 time units here, 23 to 25. So 1 plus 2, that is 3. And 9 time units here. So that's why 9 plus 3, that is 12. So 12 units of time CPU was idle, and there are 8 deltas you can see in the Gantt chart. So I have considered 8 deltas here, and out of 41, so 12 plus 8, that is 20. So 41 minus 20, so the remaining time is the actual CPU utilization. So 51% of the time the CPU was used, rest of the time CPU was not used at all. Let's discuss another question which is very similar to the earlier question. The figures are same in the question. Just one difference is I have considered all the processes will be doing the IO on same IO device. Let's say all processes wants to access the printer. Now while one process is doing the printing job and another process comes for the IO in the printer, it has to wait. That's why we say that it is a non-concurrent IO. While one is doing the IO, other has to wait till the first IO is completed. You first try to draw the Gantt chart and then look at the solution I have explained. Let me explain the solution for this question now. Let's try to draw the Gantt chart for the numerical given. As I explained, there will be burst time for every process followed by IO burst time followed by burst time again. So let me take this Gantt chart starting with time t is equal to 0. Let's keep on marking the arrived processes. So at time t is equal to 0, process P1 is arriving. At this moment, there is no process in the system, so I am going to schedule it. But here we have to consider one delta also, context switching overhead. So P1 will be actually scheduled to CPU at time t is equal to 1. As this is FCFS, which is non-preemptive, it will run for 4 units of time. It is given in the table. So it requires 4 units of time. And at time t is equal to 5, it is going for IO. Meanwhile, process P2 arrives at time t is equal to 2. So at time t is equal to 5, process P1 will go for IO. So here I am going to draw the Gantt chart for IO device also, because all processes are going to use the same IO device like the CPU. CPU is also going to be used by the same CPU is going to be used by all processes. That's why we draw the Gantt chart of CPU. Here I am going to draw the Gantt chart of IO device also. Keep in mind that the use of this IO device starts from t is equal to 5. Okay, because the first process, that is P1, which is asking the IO device, is at time t is equal to 5. Now from 5 to 15, because its IO burst time is 10, so 5 plus 10 will be 15. So at time t is equal to 15, process P1 is going to complete its IO. And at that time, it will ask for CPU again. So whenever we will reach to the time t is equal to 15 in CPU, we will consider this P1 process also. Okay. So meanwhile, process P3 also arrives at time t is equal to 4. Now at this moment, means at time t is equal to 5, P1 has left for IO and P2 and P3 are waiting. Let's schedule the P2 now by putting a delta first. So 1 time unit of delta followed by burst time of P2, which is 4 again. So from 6 to 10, P2 will execute. At time t is equal to 10, it will go for IO. But the IO, this Gantt chart says that during this time the IO device is busy. That's why the process P2 has to wait till 15 here. We cannot grant the IO device at time t is equal to 10 directly. Okay, so it will wait from 10 to 15, and at time t is equal to 15, I will schedule the process P2 to IO device. At time t is equal to 10, let's go ahead with the next process, which is P3 here. P3 will take 1 unit of time, and at time t is equal to 12, it will go for IO. Again, IO is busy, so it will wait. At time t is equal to 12, let's schedule the process P4 now by putting a delta first. It will take 4 units of time in CPU, as the table says. And at time t is equal to 17, it will go for IO. But meanwhile, in between 13 and 17, at time t is equal to 15, we know that process P1 is going to complete its IO. So while P4 is executing in CPU, process P1 has came back from IO. So at time t is equal to 15, I am going to schedule, the IO device has become idle now. And 2 processes are waiting, that is P2 and P3. That's why I am going to schedule process P2 in the IO device till 30. Because its IO burst time is 15 given in the table. So 15 plus 15 will be 30 here. And during this time, at time t is equal to 17, process P4 is arriving for IO device. So it will wait. Let's go ahead. So at time t is equal to 17, in the CPU, P1 is waiting. Now let's put a delta and allocate the CPU to P1 one more time. It will take 1 time unit as per the table. The second burst time of the process P1, that is 1 here. So at time t is equal to 19, process P1 is finishing. Now next process which is going to arrive in the CPU timeline is at time t is equal to 30, because all these three processes P2, P3 and P4 are doing the IO now. So that's why whenever this P2 will complete the IO at time t is equal to 30, it is going to come in the CPU. Now at time t is equal to 30, P2 has arrived again to ask for the CPU. So let's put a delta one more time and schedule the process. But before that, remember, whenever CPU gets IO device gets idle, so whatever be the next process waiting for IO device will be scheduled. So here after P2, after here P2, P3 arrived for IO. So that's why I have scheduled P3 here, and P3's IO burst time is 25. So 30 plus 25 is going to be 55. So at time t is equal to 55, process P3 is going to complete its IO. So at time t is equal to 30, let's put a delta and schedule the process P2. And at time t is equal to 33, the process P2 is going to complete its execution. Again from 33 to 55, no process I can schedule to CPU because both are doing IO now, P3 and P4. And at time t is equal to 55, process P3 is going to complete its IO. So let me show it. Now CPU, the IO device has again become idle, and one more process, that is P4, is waiting for IO. So let me schedule the P4 and it will run up to 58 because its IO burst time is 3 here. Alright, so let me schedule the process P3 to CPU now. So putting a delta followed by the burst time of P3, which is given as 3 time units. So 56 to 39, process P3 will execute, and at time 59, P3 is going to complete. And finally 59, meanwhile the process P4 has also completed its IO. So at time t is equal to 59, I already have the P4 available. Let's put a delta followed by the burst time of P4, which is given as 2 time units. So 60 to 62, P4 will run in CPU and it will complete its execution. So that's how, along with the CPU Gantt chart, we need to draw the Gantt chart of IO device also. If there is only one IO device, all processes are going to share. Let's calculate other factors. So as per the Gantt chart, the completion time of P1 is 19, completion time of P2 is 33, 59 and 62. The turnaround time is the 19 minus 0, completion time minus arrival time, which is 19, 33 minus 2, that is 31, 55 and 57. The total is 162, divided by 4, the average is 40.5. Let's calculate the waiting time of the process also. So waiting time is nothing but turnaround time minus total burst time. So total burst time of process P1 is 10 plus 4 plus 1, which is 15. So 19 minus 15, which is going to be the 4. Now similarly, I have calculated waiting time of all processes, and the average is 22 time units. Here is the schedule length. The last process is completing at 62. The first process has arrived at time t is equal to 0. So 62 minus 0 is the schedule length of all processes. So let's calculate the CPU utilization also. So the Gantt chart says that the total idle time is 11 plus 22 here. So the total is 33 time units the CPU has remained idle. And there I can see there are 8 deltas in Gantt chart. So total time wasted by the CPU is 33 plus 8 out of 62. and that's how I get the CPU utilization as 33.87%. So that's how we completed the numericals of FCFS. In the next session, I'm going to discuss the next scheduling algorithms, which are shortest job first and shortest remaining time first.